Greetings, this is our capstone final presentation, and the topic for our capstone project is an integrative methodology to securing IoT health applications. The group members are Emmanuel Bolderash, James Hutchins, Nak Nguyen, and Lawrence Chang. Here's a little agenda for our presentation. We're going to go over our motivations, our objective, an introduction, and following with background material. We're also going to cover our methodology and our solution overview. Finally, we're going to end up with our project schedule and the deliverables and what we've achieved this semester. Following that will be references. So here's a motivation for our capstone project. The current state of IoT security is not standardized. As such, there's existing security vulnerabilities within these devices that lead to exploits. So we seek to provide a guideline of secure implementation in regards to IoT applications through our demonstration and our integrative approach. Next slide, please. The objective of our project is to provide security for IoT health applications with a focus on data and communications between the devices. We also want to focus on the authentication of the user to the device, and finally the integrity of the data. Here's a little background. So there's an increasing trend of IoT devices, as you can see by the numbers, and these devices need to focus on the integration of existing security measures in regards to authentication and the confidentiality and the integrity of the data that's transmitted across these devices. So with all of this focus of ours, this relates most to the application layer of the OSI model, which we'll go over in the next slide. In regards to the application layer, there are existing software vulnerabilities that we will try to avoid during our implementation. And some existing vulnerabilities include buffer overflows. We also want to focus on data access permissions. So this application will have many users. As such, we want to avoid illegal users. So this is a huge focus of our capstone project, is that authentication functionality. As well as in the application layer, it handles vast amounts of data. And we also want to focus on that end-to-end encryption and how we can securely and efficiently transmit that data.
Alright, so now we talk about the application server component. This is going to be listing off the several components of our project. And in this application server, we're going to use the Google Cloud Platform. And as you can see in this diagram, we have endpoint clients, which, for example, is going to be one of our Android phones. And this will connect to the mobile backend API using the cloud endpoints. And then that will talk to our Google App Engine. And this will talk to the data and then process everything that the phone's trying to communicate with the server. Next. And here we have the database server component. We chose Amazon Web Services. Primarily, this server is going to be used for hosting a database with all of our information. And this database is going to have a table that collects heart rate, distance traveled, calories burned, and then more data as well. Next. Okay, and then here's our phone component. It'll primarily be used as a health tracker. It'll be used to track health data and then store it securely in the cloud database. The features that it's going to have is third-party login authentication and transport layer encryption with cloud service. Then here we have our watch component. It'll collect and transmit data to the smartphone using Bluetooth, device-to-device communication. And specifically, it'll be collecting the heart rate data and the calories burned. Alright, so here we have our network model, and as you can see from the diagram, we have several of our components. We have over here in this cloud the application server that'll be hosted on Google's App Engine cloud platform. Then on the far right, we have database server that'll be hosted on Amazon's Web Services. Here we have the user, the smartwatch, which will be our Fitbit watch, and then we have our smartphone running Android. So as you can see, the communication between these components, we have the application server communicating to the database server. It'll be querying and asking for input into the database. Then we have the second communication we have between the smartphone and the smartwatch. It'll be Bluetooth, and that'll be gone over more in depth in upcoming slides. Then we have the third one, we have smartphone to the application server. This will be through HTTPS, secure communication. And then lastly, our other part is the authentication of the user to the smartphone so that it could be authenticated with the application server. And that'll be using Facebook login, and that'll also be gone more in depth. And then here we have the first one. First part of our methodology is going to be integrity of our data. And to ensure that, we're going to be using features provided by Amazon Web Services, namely Amazon S3 managed encryption keys. What this will do is server-side encryption for data at rest. Also, we'll use access control list, which is also included in Amazon Web Services. What this will do is grant us control for read-write privileges of user data. And then we will hash our data as well for increased integrity so that we can certify uncorrupted transmission with hash values. Second part of our methodology is phone to watch communication. It'll only be using Bluetooth, as that's the only thing that's available for the Fitbit watch. And what this will do is it'll have a secure paired connection between the watch and the smartphone, and it'll be using ad hoc APIs such as the Android Bluetooth API.
Alright, so this is our third part of our methodology correlating to the network graph that our system diagram you saw earlier. So this is our phone to server component. So we wanted to consider what protocols to be using in this kind of IoT environment, and two were the most common were looked at. So that would be HTTPS and then CoAP, which stands for Constrained Application Protocol. So we looked at several areas. We looked at the power efficiency, and we can see that CoAP is much more efficient in using power than HTTPS. Also looking at header size, CoAP had a smaller header size, 8 bytes compared to the 20. And then we looked at security capabilities. So HTTPS, you can see it has built-in TLS, transport layer security, and IP security. However, in CoAP, we would have to implement our own. Reliability-wise, HTTPS is connection-based, so packet recovery it'll recover dropped packets, while UDP is connectionless, thus more packets will just be sent out rather than a stream. And considering all these areas, we wanted to focus most on security and reliability. And so we chose HTTPS for that because it matched our primary objectives of the project. If we were concerned about maybe smaller devices such as household appliances in the IoT environment, because those have restrained resources, maybe then we would also consider CoAP, but because we're working with smartphones, those have a comparable processing power to computers nowadays. So we chose HTTPS for the protocol we would be using to communicate between our phone and server. We can see here some of the points considered. Security capabilities, as mentioned before, it uses TLS, and reliability for data transmission. So number 4 of our methodology is the user authentication to the phone application. How did we want to go about doing that? So we looked at a couple different things: social login versus the traditional registration. We also considered biometrics. However, this was not feasible due to the hardware limitations. Traditional registration was also considered. However, it would require us to actually host our own database, protect that, and that was something that we believed we didn't have the resources for, especially for this big of a project. So we decided to, why not use some other companies' well-known, trusted services to authenticate our users. As we can see here, a recent market research called Consumer Perceptions of Online Registration Social Login actually showed that 77%, a large majority of the 657 surveyors actually preferred single sign-on or SSO to be offered by websites. They like the idea of having one account for multiple services. And so and then we looked more into this, and as of 2012, Facebook login was the most popular. So we of course considered Google login, Twitter login, a lot of other services offer this kind of single sign-on, but Facebook by far was the most popular, and thus we thought it would reach out to a larger population, so we decided to go with Facebook login. Next slide. And elaborating more on that, what is Facebook login? So Facebook login, again, was chosen to accommodate the large user base that uses it. It uses an OpenID-like authentication system, and including built on top of OAuth, which we'll go later on. And then it features single sign-on. So that means if the user is already signed into Facebook, through Facebook they would be signed into our application. So it shares intent with the native Facebook application, and we assume Facebook is this trusted third party. So all this can be integrated using Facebook APIs. So there are 3 authentication scenarios when it comes to logging into Facebook. The first is if you have the Facebook application installed, the native application on your phone, and you're already logged into that. In that case, when you try to log into our application, it will automatically see, oh, I'm already logged into Facebook, thus logging you into the application. The second scenario is if you have the Facebook application, but you are not logged in currently. What happens then is trying to log on, once you open our app, it will redirect you to Facebook's login page, therefore opening the Facebook application. Therefore, you log in through Facebook and log in through the application. Finally, the last scenario is what if Facebook is not installed on your phone? In that case, it will open your default browser such as Google Chrome or Safari, and then it will default to the web view and ask you for authentication to your Facebook. Upon successful login, Facebook will initiate the OAuth protocol, or basically an authorization protocol asking, can this application, in this case our application, our health application, can it access Facebook resources? And so acceptance will close out of the Facebook app and redirect you to our application, thus authorizing Facebook to access, or thus also authorizing our application to access Facebook's resources such as email, user accounts, whatnot.
We broke the tasks up into 6 major categories and split those up amongst the group to get everybody able to do work and do an equal amount of work. You can see who is doing the work on the left from my point of view, right from the cameras, and you can see what is being done on the right. For this fall semester, we did research and we made an initial design for our IoT network, which included a smartwatch, a smartphone, and a server, as mentioned earlier. We also plan to implement all of this over winter break and early January. So in January and February, our hope is to have the application finished, and we will go through debugging the application to figure out what has been working, what has not been working, and fix anything that needs to be fixed. In March and April, we will have everything done. We'll have the presentation and the write-ups, all of that turned in. So what our deliverables are is we're going to deliver a fully functional network, which includes the server, the watch, and the phone application. We will have communication between each of those that is secure, so it's safe to send the information between them. We will have a report, poster, and demonstration also prepared, and those will be turned in. So these are our references that were used throughout the slides, and thank you.